Reality has more layers than you can see. The universe contains hidden dimensions, a concept that has evolved from ancient philosophy to modern physics. You will learn the complete story of this cosmic evolution and see how it could solve mysteries like dark energy and the origin of everything. How did we go from a three-dimensional world to the brink of discovering unseen realms? What if gravity is weak because it leaks into a higher dimension? We will trace this epic quest through revolutionary ideas and brilliant minds. By the end, your perception of reality itself will be transformed. What does it mean for our universe to be written in more than 3 dimensions? The story of hidden dimensions begins not with equations, but with a question posed in firelight. Ancient philosophers gazing at the stars wondered if what they saw was the whole truth. Plato, in his famous allegory, described prisoners chained in a cave, seeing only shadows cast on a wall by a fire behind them. To those prisoners, the flat, flickering shadows were the entirety of reality. Plato suggested we might be like those prisoners, perceiving only a crude projection of a truer, richer world existing in a higher realm. This was a philosophical, not a scientific, idea, but it planted a crucial seed. What if our three-dimensional experience is just a shadow of something more complete? Meanwhile, other thinkers like Democritus pondered the nature of empty space, or the void, questioning whether it was merely an absence or a thing with its own properties. For centuries, these ideas simmered, beautiful thought experiments waiting for a language to make them tangible. That language arrived through pure mathematics. For over 2,000 years, the geometry of Euclid, with its flat planes and parallel lines, was considered the absolute description of reality. But in the 19th century, mathematicians like Carl Friedrich Gauss and, most profoundly, Bernhard Riemann began to ask a revolutionary question. What if space itself could be curved? Riemann developed a new geometry that described spaces of any number of dimensions, spaces that could be warped and folded like fabric. This was a staggering leap. Mathematicians were no longer just describing the world as it appeared. They were inventing the tools to describe worlds that could not be seen or even imagined physically. They were building the playgrounds, the abstract arenas, where higher dimensional realities could be explored on paper. This work was a quiet revolution, proving that the human mind could conceive of structures beyond sensory experience. It transformed the philosophical musing of Plato's cave into a precise, calculable framework. The stage was now set, waiting for a physicist to step in and ask, what if these mathematical playgrounds are not just fictions, but blueprints for our actual universe? Then came a mind that would weave these threads into the fabric of reality itself. Albert Einstein entered the 20th century with a vision that would shatter the static universe. He proposed a radical idea: space and time were not separate entities. They were fused into a single, dynamic entity he called spacetime, a 4-dimensional continuum. Think of it not as a stage where events play out, but as a vast, stretchable fabric. The sun, the earth, all objects with mass do not simply sit in this fabric. They press down into it, creating curves and depressions. What we perceive as the force of gravity, Einstein revealed, is simply the motion of objects following the contours of this warped geometry. A planet orbits a star not because it is pulled by an invisible string, but because it is rolling along a curved groove in the cosmic fabric. This was the general theory of relativity, and it was the first true evolution in our understanding of dimensions. Time was no longer a universal ticker in the background. It was a legitimate dimension, inextricably woven with the three of space. The universe became a 4-dimensional manifold, a shape that could bend and ripple. This monumental unification proved dimensions could interact. They could have geometry, they could be dynamic, but a profound question lingered in the wake of this triumph. If our reality is a four-dimensional fabric that can curve, could that fabric itself be embedded within something even larger? The success of Relativity did not close the book on cosmic architecture. It merely turned the page, inviting physicists to look for the hidden lines of text, the subtle folds in the manuscript of reality. Einstein's four-dimensional fabric was a masterpiece, but it left a thread dangling. Gravity was beautifully described, but another fundamental force, electromagnetism, remained stubbornly separate. The dream of a single, elegant theory that could describe all of nature's forces was alive, and it would lead to one of the most daring leaps in the history of physics. In the 1920s, a mathematician named Theodore Kaluza looked at Einstein's equations for gravity and made a stunning proposal. What if we simply rewrote them, not for 4 dimensions, but for 5? He took the bold step of adding a single, unseen dimension to the fabric of spacetime. At first, this seemed like a mathematical trick, but the result was nothing short of miraculous. When Kaluza solved his 5-dimensional equations, something extraordinary happened. They did not just describe gravity, they naturally split apart, revealing the precise equations for both Einstein's gravity and James Clerk Maxwell's theory of light and electromagnetism. It was as if, by viewing reality from a slightly higher vantage point, 2 seemingly different forces were revealed to be different facets of a single, unified phenomenon. But this raised an obvious and critical question. If there is a 5th dimension, where is it? Why can't we see it or move through it? This is where physicist Oscar Klein entered the story. He provided the crucial physical interpretation. Klein proposed that this extra dimension was not large and expansive like the 3 dimensions of space we know. Instead, it was curled up or compactified into an unimaginably tiny circle, a loop so small that its circumference was far smaller than an atom. To understand this, picture a long, thin garden hose. From a great distance, it looks like a simple one-dimensional line. But if you could shrink yourself down to the size of an ant and walk up to it, you would discover its 2nd dimension, the circular direction that wraps around its surface. Klein argued our universe might be like that hose. At the scale of our everyday lives, we only perceive the large, extended dimensions. The 5th dimension is curled so tightly that we are, in effect, perpetually at that great distance, unable to perceive its circular nature. He even calculated its possible size, linking it to the emerging world of quantum mechanics. This idea, now called Kaluza-Klein theory, was a watershed moment. It transformed hidden dimensions from a philosophical or mathematical curiosity into a potential physical reality with a concrete job to do, unifying nature's forces. It was the first serious proposal that the architecture of our cosmos might be written in more than 4 dimensions. The scientific community was intrigued but ultimately skeptical. The theory had difficulties, and with no way to test for such a tiny, hidden dimension, the idea was largely set aside. Yet it planted a seed of profound possibility. It demonstrated that extra dimensions were not just a wild speculation. They were a powerful tool that could solve deep puzzles about the unity of nature. That seed would lie dormant in the soil of theoretical physics for decades, waiting for the right conditions to sprout into something even more ambitious and strange. Yet the universe, it seemed, was written in 2 very different languages. While Einstein's general relativity painted the cosmos with the broad, elegant strokes of warped spacetime, a revolution was brewing in the opposite direction, inward toward the impossibly small. Quantum mechanics emerged not from grand cosmic visions, but from the stubborn, flickering behavior of light and atoms. Its world was one of radical uncertainty, where particles were also waves, existing in a haze of probabilities rather than definite positions. An electron could, in a very real sense, be in many places at once until observed. empty space itself was not empty, but a seething quantum foam, a frenzy of virtual particles blinking in and out of existence. This theory was breathtakingly accurate, predicting the behavior of the subatomic world with uncanny precision. But it operated firmly within the old, flat, three-dimensional stage of Newton, treating space as a passive container. This created a profound and embarrassing schism at the heart of physics. The two most successful theories ever devised, each master of its own domain, were utterly incompatible. General relativity described gravity as the smooth curvature of a four-dimensional fabric. Quantum mechanics described particles as probabilistic excitations in fields. When physicists tried to combine them to describe gravity with quantum rules, the mathematics exploded into infinities and nonsense. It was as if the universe had two rule books, one for the very large and one for the very small, and they gave contradictory instructions for the same game. This was not just a technical problem, it was a crisis of understanding. It screamed that our picture of reality was fragmented, that some crucial piece of the puzzle was missing. Many began to suspect that piece was dimensional. Perhaps the bizarre, probabilistic nature of quantum mechanics and the geometric certainty of gravity were not opposing truths, but different shadows cast by a single, more complex object existing in a higher dimensional reality. The smooth fabric of spacetime in relativity and the fuzzy probabilities of the quantum world might simply be different perspectives, like seeing a three-dimensional cube as either a square or a hexagon depending on your angle. The failure to unite them hinted that both theories were approximations of a deeper, more complete description written in more dimensions. This crisis, this quantum conundrum, created a vacuum, a silent plea for a new kind of idea. It was into this intellectual void that a radical, beautiful, and immensely complex framework would eventually step, one that dared to suggest the answer lay not in 4 dimensions or 5, but in 10 or even 11. The crisis of incompatibility demanded a solution of breathtaking audacity. From the mathematical wilderness, a new candidate emerged, one so radical it redefined the very notion of a fundamental particle. This was string theory. It proposed a simple yet profound shift in perspective. Forget the idea of infinitesimal, zero-dimensional points as the bedrock of reality. Instead, picture the universe's most basic ingredients as unimaginably tiny, one-dimensional loops or strands of pure energy, vibrating filaments so small that if an atom were the size of our solar system, a string would be no larger than a tree on Earth. In this vision, everything in existence, every electron, every quark, every photon of light is not a point but a string. And crucially, the properties of each particle are dictated not by what it is, but by how it vibrates. Think of a violin string. Plucked one way, it produces a specific note, a clear tone. Plucked another way, it produces a different note. In string theory, the universe's strings are like that. One specific pattern of vibration might correspond to an electron with its particular mass and negative charge. A different vibrational mode, a different note in this cosmic symphony, might manifest as a quark or as the particle that carries the force of gravity, the graviton. This elegant idea promised a stunning unification. All matter and all forces could be understood as different melodies played on the same fundamental strings. But this beautiful vision came with a staggering, non-negotiable requirement. The mathematics governing these vibrating strings only produced sensible, consistent results, free of the infinities that plagued other theories, under one specific condition. The universe could not have only the 4 dimensions of spacetime we experience. For the equations to balance, for the symphony to be in tune, string theory demanded more space to breathe. Initially, the framework required a total of 10 dimensions. Later refinements, in a more powerful version called M-theory, pointed toward 11. So where are these extra 6 or 7 dimensions? They follow the path first suggested by Kaluza and Klein, but on a far more intricate scale. They are compactified, curled up into fantastically complex, tiny geometric shapes known as Calabi-Yau manifolds. Picture the three large dimensions of space as the expansive length of a garden hose. Now, imagine the cross-section of that hose is not a simple circle, but a fantastically sculpted, multi-looped shape with holes and tunnels, a shape with its own rich topology. That sculpted cross-section represents the hidden dimensions, folded into a space so minute that it is woven into the fabric of every single point in our familiar three-dimensional world. This was the monumental evolution string theory represented. Hidden dimensions were no longer just a clever trick to unify two forces or a philosophical speculation. They became an absolute necessity, the foundational architecture required for the internal consistency of a potential theory of everything. The stage of reality was not a simple four-dimensional fabric, but a 10 or 11-dimensional arena where the vibrational patterns of strings dictated the laws of physics themselves. The question shifted from whether extra dimensions exist to what specific shape they take, for the geometry of those hidden folds would determine everything from the number of particle types to the strength of the forces that bind our universe together. The geometry of these hidden dimensions is not a chaotic tangle. It is an exquisite, specific architecture known as a Calabi-Yau manifold. To grasp this, picture our familiar three-dimensional space as a vast straight line. Now imagine that at every single point along that line, like an infinite string of pearls, there is not a dot but an entire, fantastically complex shape. This shape is the Calabi-Yau manifold, a six-dimensional object curled into a space a billion times smaller than an atom. It is the hidden cross-section of reality. While we cannot visualize six dimensions, we can understand its properties. Think of it as a hyper-dimensional donut, but one with a multitude of holes and tunnels, a labyrinthine sculpture of pure geometry. Its form is not random. It is a solution to some of the most elegant equations in mathematics, a shape of perfect balance and stability first proven to exist by mathematician Xing-Tung Yau. And here lies the staggering connection. The specific topology of this tiny, hidden shape, the number of holes it has, the way its surfaces twist and connect, acts as a cosmic tuning board for the vibrating strings. It determines how many ways a string can vibrate, which in turn dictates the fundamental laws of our universe. The number of particle families, the existence of the electron and its specific mass, the strength of the electromagnetic force compared to gravity, even the potential presence of dark matter candidates, all of these seemingly arbitrary features of our reality could be direct readouts from the geometric code of the Calabi-Yau manifold. This transforms our view of the cosmos. The diversity we see, from the particles in your hand to the forces shaping galaxies, is not a collection of separate ingredients. It is the rich, multidimensional echo of a single, hidden shape. Exploring these manifolds is not just abstract mathematics. It is akin to discovering the cosmic DNA, the elegant blueprint from which all physical phenomena are expressed. The quest now becomes a deeply beautiful one, to listen to the symphony of our universe and work backwards, to deduce the shape of the instrument upon which it is played. But what if the hidden dimensions are not curled into a tiny knot at every point? What if they are vast, even infinite, and we simply cannot access them? This is the startling proposition of Brane world scenarios, a revolutionary twist that emerged from the deeper currents of string theory. It begins with a simple yet profound shift in perspective. Our entire four-dimensional universe, all of galaxies, stars, and planets, might not be an isolated island. Instead, it could be a three-dimensional membrane or a brane, floating like a vast, impossibly thin sheet within a much larger, higher-dimensional space called the bulk. Think of our observable cosmos as a single page in a colossal, multidimensional book. We live our entire existence confined to that page, able to move freely across its length and width, but utterly unaware of the other pages stacked above and below us in the bulk. This idea provides an elegant answer to a persistent question. If extra dimensions exist, why are they hidden? In the Brane world picture, the answer is confinement. All the particles and forces that make up our everyday world, the electrons and photons and quarks, are like ink printed firmly onto our page. They are stuck to our brain, unable to detach and move off into the bulk. This is why we only directly perceive 3 dimensions of space and 1 of time, because everything we are made of and everything we interact with is bound to this membrane. There is, however, a dramatic exception. Gravity, the curvature of spacetime itself, might not be bound by the same rules. In many Brane world models, the gravitational force is free to leak off our brain and seep out into the surrounding bulk. This offers a breathtakingly simple potential explanation for one of physics' great puzzles: why gravity is so astonishingly weak compared to the other fundamental forces. A magnet the size of a coin can lift a paperclip, defeating the gravitational pull of the entire planet Earth. If gravity's influence is not confined to our brain but diluted as it spreads into the extra-dimensional bulk, its apparent feebleness in our world makes perfect sense. This vision, championed by theorists like Lisa Randall and Raman Sundram, dramatically evolved the narrative. Hidden dimensions no longer had to be microscopic. They could be large or even infinite in extent, existing right alongside us in a direction we are fundamentally unable to point toward. This opens a vista of mind-bending possibilities. If our universe is one brain floating in a higher dimensional sea, could there be others? The bulk might be populated by a multitude of parallel brains, each a complete universe with its own stars, its own laws of physics, drifting silently in the dark. We might never touch them, but their gravitational influence could subtly brush against our own. Some have even speculated that a rare, cataclysmic collision between 2 such brains could explain the Big Bang itself, a cosmic shudder that ignited our entire reality. Others see in this framework a new path to understanding the mysterious dark energy accelerating the expansion of the cosmos. The Brane world concept pushes the boundaries of cosmological thought, transforming hidden dimensions from a compactified footnote into the vast, unseen ocean in which our island of reality floats. This profound weakness of gravity is not just a curious fact, it is a screaming anomaly known as the hierarchy problem. If nature's forces were truly unified at the birth of the cosmos, emerging from a single, symmetric origin, logic suggests they should be of comparable strength. Yet gravity is weaker than the electromagnetic force by a factor of 1 followed by 40 zeros, an almost unimaginable disparity. It is the faintest whisper against a roaring symphony. For decades, this staggering imbalance had no clear explanation. It was simply accepted as a bizarre, fine-tuned parameter of our universe, a cosmic accident written into the laws. But the evolution of hidden dimension theories reframes this entire mystery. It suggests the weakness is not a random flaw in the design, but a profound clue to the architecture of reality itself. In models with large extra dimensions, gravity behaves differently because it is the only force not confined to our 3-dimensional brain. While particles of light and matter are stuck to our membrane, the graviton, the hypothesized carrier of gravity, can leak off into the higher dimensional bulk. Imagine a single drop of ink placed on a tightly stretched sheet of plastic. From the perspective of a tiny ant living on that sheet, the ink forms a dark, concentrated stain. But if that sheet is suspended in a vast tank of water, the ink will slowly diffuse outward, spreading through the entire volume. To the ant, the stain appears to fade, to weaken dramatically, because its essence is now diluted in a space it cannot perceive. This is the elegant geometric solution offered by Brane world cosmologies. Gravity seems weak to us not because it is inherently feeble, but because its true strength is spread thin across dimensions we are blind to. Our entire universe is that ink stain, experiencing only a faint shadow of gravity's full intensity. This transforms the hierarchy problem from an unanswered question into a potential doorway. The apparent weakness of gravity ceases to be an arbitrary number in an equation and becomes a measurable signature, a direct consequence of the unseen geometry in which our world is embedded. It turns a puzzling parameter into a cosmic cartographer's tool, hinting at the vast, hidden landscapes that lie beyond our perception. This grand synthesis of micro and macro physics leads us to the most profound implication of all, the fate of the cosmos itself. The hidden dimensions are not a static backdrop. They are dynamic players in the cosmic drama, evolving alongside the universe from its first instant. To understand this, we must revisit the earliest moments, a period of unimaginable expansion called cosmic inflation. In a fraction of a second, the universe ballooned from smaller than a proton to a vast, smooth expanse. What could have powered such a violent, precise growth? Some compelling theories point directly to the extra dimensions. Picture the Calabi-Yau manifold, that intricate, six-dimensional shape curled at every point. In the searing heat of the newborn universe, this shape may not have been stable. It could have been vibrating, twisting, seeking its equilibrium. The energy released as these hidden dimensions settled into their final, stable configuration, a process called stabilization, could have been the engine that drove inflation. It is a breathtaking idea that the unfurling of unseen geometric spaces provided the kick that set our entire visible universe in motion, but the influence does not end there. The story continues across nearly 14 billion years to the present day, and to the greatest mystery in modern cosmology, dark energy. We have observed that the expansion of the universe is not slowing down as once expected, but accelerating. Something is pushing galaxies apart with ever-increasing speed. This repulsive force, dubbed dark energy, constitutes the majority of the universe's content, yet we have no idea what it is. Here, the hidden dimensions offer another compelling clue. The vacuum of space is not truly empty, it hums with quantum energy. In our familiar 3 dimensions, calculations of this vacuum energy produce a number catastrophically large, one that would have torn the universe apart long ago. This is the infamous cosmological constant problem. But if our reality is embedded within higher dimensions, the story changes. The total vacuum energy is a sum of contributions from all dimensions, both the large ones we see and the tiny, curled-up ones we do not. It is possible that the precise geometry and evolving energy of the compactified dimensions provide a delicate, near-perfect cancellation, leaving behind only the faint, positive residue we detect as dark energy. In this view, dark energy is not a new, exotic substance. It is the long-term echo, the slow bleed of energy from the hidden dimensional geometry as it subtly adjusts over cosmic time. The cosmological constant, a term Einstein introduced and later called his greatest blunder, may find its true physical origin not in our 4-dimensional world, but in the quiet dynamics of the higher dimensional bulk. This connection is the ultimate evolution of the idea, binding the destiny of the entire cosmos, the acceleration of every galaxy, to the microscopic vibrations and stability of shapes a billion times smaller than an atom. The largest questions we can ask are written in the smallest script imaginable. The grandest ideas in physics must ultimately face the test of reality. How do we search for something as elusive as a hidden dimension? We cannot simply build a higher dimensional microscope. Instead, scientists have become cosmic detectives, devising ingenious experiments to look for the fingerprints these unseen realms would leave on our world. The search unfolds on 2 wildly different scales. from the violent collisions of the subatomic to the exquisitely delicate measurements of forces between objects you could hold in your hand. At the Large Hadron Collider, the most powerful particle accelerator ever built, protons are smashed together at nearly the speed of light, recreating conditions not seen since the universe's first moments. In this microscopic fireball, physicists are not just looking for new particles, they are looking for missing pieces. If extra dimensions exist, some of the energy from these collisions could vanish, carried away by particles like gravitons that slip off our brane and into the bulk. Detecting this missing energy would be a profound clue. Even more dramatic is the hunt for microscopic black holes. If gravity's true strength is revealed at tiny distances within these extra dimensions, the collider's immense energy could, for a fleeting instant, warp spacetime enough to create a black hole smaller than an atom. It would evaporate instantly in a shower of characteristic particles, a signature that would be unmistakable. So far, the collider has not seen these signals, but every scan of the data, every null result, is not a failure. It is a measurement that tells us the hidden dimensions, if they are there, must be smaller or more tightly wrapped than a certain scale. We are drawing the boundaries on the map of possibility. On the other end of the scale, other experiments probe the force of gravity itself with breathtaking precision. If there are large extra dimensions, their presence would alter how gravity behaves over tiny distances. Newton's law of gravity, which states the force weakens with the square of the distance, might break down at scales smaller than a millimeter. To test this, scientists use devices of incredible sensitivity, like finely balanced pendulums or vibrating crystals, to measure the gravitational pull between two objects as they are brought within a hair's breadth of each other. They are essentially weighing the force of gravity in a realm where the influence of hidden dimensions might finally peek through. These experiments are quiet, meticulous, and just as revolutionary as the giant collider. They probe the universe not with brute force, but with a whisper, listening for the subtle sigh of gravity leaking into another realm. While direct, undeniable evidence remains just beyond our grasp, this entire experimental pursuit represents a crucial evolution. We are no longer just dreaming in equations. We are actively interrogating the cosmos, using the predictions of these beautiful theories to guide our instruments. Every experiment, whether it finds a signal or sets a new limit, carves away at the space of possibilities, refining the blueprint for reality's hidden architecture. The search itself transforms the question from a philosophical fantasy into a tangible, empirical science. Yet this beautiful geometric vision brings with it a profound and unsettling consequence. As physicists explored the intricate mathematics of Calabi-Yau manifolds, they made a startling discovery. There was not one unique solution, not one perfect shape for the hidden dimensions. Instead, the equations pointed to a staggering number of possible stable configurations, a number so vast it defies human comprehension, on the order of 10 to the power of 500. This is the landscape problem. Each distinct way of curling up those 6 extra dimensions represents a different possible universe, each with its own unique set of physical laws and fundamental constants. In one configuration, the strings might vibrate to produce a universe where gravity is strong and stars burn out in an instant. In another, electromagnetism might be too weak to form stable atoms, preventing matter from coalescing at all. Our universe, with its specific particle masses and force strengths perfectly suited for galaxies, planets, and life, would be just one tiny island in this incomprehensibly vast cosmic archipelago. This realization represents a dramatic evolution in the quest. Hidden dimensions may not lead us to a single, elegant theory of everything, but to a near-infinite landscape of possible everythings. This addresses one of the deepest mysteries in cosmology, the fine-tuning problem. Why do the constants of nature seem so exquisitely balanced to allow for our existence? If a multiverse exists, then the answer shifts. We do not live in a universe fine-tuned for life. We simply live in one of the rare universes within the multiverse where the dice rolled in such a way that life became possible. This is known as the Anthropic Principle. While this idea offers a philosophical answer, it presents a serious scientific challenge. If a theory predicts every possible outcome, can it truly predict anything specific about our own world? The dream of a single equation that uniquely describes our reality seems to recede into this sea of possibilities. Yet this shift is not an end but a transformation of the quest. The focus moves from finding the one fundamental equation to understanding our place within a potentially infinite ensemble. It asks us to consider whether the hidden dimensions are the architects of a single cosmos, or the seeds from which a multiverse eternally blossoms. The search for evidence then becomes even more crucial, a hunt for any signature in our universe that might hint at its neighbors in the landscape, a faint echo from another island in the dark. The landscape of possibilities is vast, but not every path through it leads to unseen realms. While string theory weaves its vision in 10 or 11 dimensions, another profound framework charts a radically different course. This is loop quantum gravity, a compelling alternative that seeks to unite quantum mechanics and general relativity without invoking a single extra dimension. Its starting point is a breathtakingly simple yet profound idea. What if spacetime itself is not a smooth, continuous fabric, but is woven from individual threads? In this picture, the universe at its most fundamental scale is not a void, but a dynamic network of interwoven loops, a cosmic tapestry of pure relationship. These loops are the quanta of space, the smallest possible pieces of geometry, existing at the unimaginably tiny Planck scale. Where general relativity describes a bendable continuum, loop quantum gravity proposes that space is granular, composed of discrete grains, much like a digital photograph is made of individual pixels. This granularity emerges naturally from the mathematics, solving the old problem of infinities that plagued earlier attempts to quantize gravity. The theory successfully describes gravity within the familiar 4 dimensions of spacetime, rebuilding geometry from the ground up as a quantum phenomenon. It paints a universe where space is not a container but a spin network, an evolving web where each intersection carries a tiny volume and each link represents a quantum of area. This creates a startling vision of the Big Bang. Instead of a singular point of infinite density, loop quantum gravity suggests a cosmic bounce. The universe could have emerged from a prior phase of contraction, a rebound from a supremely dense but finite state, avoiding the mathematical breakdown of the singularity entirely. The tension between these two grand frameworks, string theory and loop quantum gravity, represents a critical divergence in the evolution of theoretical physics. One adds dimensions to achieve harmony, viewing particles as vibrations in a higher dimensional arena. The other subtracts the assumption of continuity, viewing spacetime itself as a quantum structure woven in 4 dimensions. This is not a weakness in our pursuit of truth, but a tremendous strength. It forces the most rigorous questioning. Are extra dimensions a physical necessity of reality, or are they a powerful mathematical convenience, a particular lens that brings certain features into focus? This competition enriches the entire field, ensuring that every assumption about the fundamental nature of reality is stress-tested from completely different angles. Both approaches are monumental efforts to listen to the universe's deepest whispers, and in their stark disagreement, they guide us toward a more complete, and perhaps more surprising, understanding of the cosmic architecture. The most radical evolution in this story may dissolve dimensions altogether. It begins with a black hole, the ultimate cosmic paradox. When an object falls into a black hole, it seems all information about it is lost forever, violating a sacred principle of quantum mechanics. To resolve this, physicist Jacob Bekenstein and later Stephen Hawking made a startling discovery. They found that the maximum amount of information, or entropy, a black hole can contain is not proportional to its volume, but to the area of its event horizon, its two-dimensional surface. It is as if everything within a three-dimensional space is painted onto its two-dimensional boundary. This insight blossomed into the holographic principle, a concept that turns our intuition about reality inside out. The principle proposes that all the information describing everything within a volume of space, every star, every atom, every vibration, can be fully encoded on the lower dimensional boundary that encloses it. Think of a hologram on your credit card. It is a flat, two-dimensional sticker, but when light shines on it, it projects a seemingly three-dimensional image with depth and perspective. The holographic principle suggests our entire universe might work the same way. The three-dimensional world we experience, with all its richness and solidity, could be a magnificent projection. The true, fundamental description of reality might be written on a vast, distant, two-dimensional surface at the edge of the cosmos. In this view, the hidden dimensions of string theory, and even the familiar dimensions of space itself, are not the primary stage. They are emergent phenomena, like the three-dimensional image emerging from the flat hologram. This idea finds a precise mathematical form in a discovery known as ad-SCFT duality from the world of string theory. It shows a perfect equivalence, a dictionary, between a theory of gravity operating in a certain higher dimensional space and a quantum field theory, without gravity, operating on its lower dimensional boundary. One reality, two perfectly equivalent descriptions. This blurs the very definition of a dimension. Is our world fundamentally three-dimensional, or are the three dimensions just a useful way to organize information that is fundamentally stored in two? The holographic principle suggests that the number of dimensions we perceive might not be a fixed feature of the universe, but a consequence of our descriptive framework, a language we use to make sense of the cosmic code. It is an evolution that questions the solidity of space itself, proposing that the stage of reality is not a given, but a grand and breathtaking illusion. But what if the hidden layers are not only in space? Our journey has explored the curling up of spatial dimensions, but what about the one dimension we feel flowing in a single, irreversible direction? Time itself may hold secrets. We are accustomed to thinking of time as a solitary line, a one-way street from past to future. Yet some physicists like Itzhak Bars have dared to propose a radical extension. What if our universe possesses not one, but two dimensions of time? This is not a proposal for building a time machine or revisiting yesterday. It is a mathematical suggestion that the fundamental laws we observe, the rules governing particles and forces, might be projections from a more complete and symmetric reality existing in a higher dimensional spacetime that includes multiple temporal directions. In this richer arena, the strange probabilities and uncertainties of quantum mechanics, where particles seem to exist in blurred states, could find a natural, deterministic explanation. They would appear fuzzy and uncertain only because we are seeing a lower dimensional shadow of a clearer, more defined process happening in the full higher dimensional realm. Even the arrow of time, the relentless drive from order to disorder that gives us a sense of past and future, might emerge from this more complex temporal geometry. Perhaps our one-way experience of time is not a fundamental law, but a consequence of how our particular slice of reality is oriented within a timeless, multi-temporal bulk. This idea represents a profound evolution in the concept of a dimension itself. It challenges the bedrock intuition that time is singular and flowing. It asks us to consider that the stage of reality might have more than one kind of backstage, more than one direction in which causality can unfold. If time has hidden layers, then our entire narrative of cause and effect, of history as a single thread, might be a simplified story. The true chronicle of the cosmos could be written in a richer language, one where events are connected not along a single line, but across a temporal tapestry we can barely conceive. This frontier stretches our imagination further than extraspatial dimensions ever could, because it questions the very medium through which we experience existence. It suggests that the flow we feel, the ticking of every clock, might be the most compelling and intimate illusion of all. Our struggle to see beyond our own dimensional limits is not new. Over a century ago, a story was written that perfectly captures this human predicament. It is called Flatland, a mathematical romance by Edwin A. Abbott. In this fictional world, everything exists in only two dimensions. The inhabitants are geometric shapes, triangles, squares, circles, living on an endless flat plane. They have no concept of up or down, only forward, backward, left, and right. To them, a three-dimensional object like a sphere passing through their plane would appear as a mystery. It would first manifest as a single point that grows into a circle of increasing size, then shrinks back to a point before vanishing entirely. To a Flatlander, this is an incomprehensible event, a shape magically changing size and then disappearing. They lack the perceptual framework to understand a sphere simply moving through their two-dimensional slice of reality. We are the Flatlanders of our own cosmos. Our brains and senses evolved to navigate a world of length, width, and height. A true fourth spatial dimension, or a curled-up Calabi-Yau manifold, is as invisible and conceptually baffling to us as the sphere was to the square. This classic metaphor elegantly illustrates why extra dimensions are so difficult to grasp. They literally lie outside our field of experience, but our tools for understanding have evolved alongside our theories. Today, we have a new, powerful metaphor drawn directly from modern technology, virtual reality. When you put on a VR headset, you are immersed in a convincing, three-dimensional world. You can look around a digital landscape, reach out toward virtual objects, yet this entire experience is generated by two small, flat screens, one for each eye. Your brain interprets the two slightly different two-dimensional images and constructs a compelling illusion of depth and volume. In a profound sense, the three-dimensional VR world is a projection, a shadow cast by the two-dimensional screens. Now extend this idea. What if our rich, tangible, three-dimensional universe, with its galaxies and oceans and mountains, is itself a projection? What if it is a magnificent, immersive hologram generated from information encoded on a distant, two-dimensional boundary, as the holographic principle suggests? Or perhaps it is the dynamic interface of a three-dimensional brain moving through a higher dimensional bulk. These technological metaphors do more than just explain, they transform public understanding. They take esoteric mathematics and translate it into a sensory, relatable experience. They remind us that our perception is not a window onto absolute truth, but a user interface evolved for survival in a specific environmental niche. The true nature of reality, with its hidden folds and vibrational strings, may be as far beyond our innate perception as a symphony is to someone who has only ever felt vibrations through the floor. Embracing these metaphors fosters a vital scientific humility. They encourage us to question the solidity of the stage upon which we stand and to remain passionately curious about the deeper architecture waiting to be discovered. By leveraging the familiar, we train our minds to imagine the genuinely unimaginable, to sense the hidden contours of the cosmos not with our eyes but with our intellect. These ideas do more than reshape our physics. They challenge the very foundations of how we know what is real. If the truest description of the universe requires dimensions we can never see or touch, in what tangible sense do they exist? This question echoes a centuries-old philosophical debate. On one side is realism, the view that scientific theories describe a world that exists independently of our minds. If the equations of string theory or the geometry of a Calabi-Yau manifold are consistent and powerful, a realist would argue they reveal genuine features of reality, whether we perceive them or not. The other side, instrumentalism, sees theories merely as useful tools for making predictions about what we can observe. From this view, extra dimensions are a brilliant mathematical instrument, a convenient fiction that helps us organize the data from particle colliders and telescopes, but not necessarily a literal truth. The evolution of these theories pushes us toward a fascinating middle ground. It suggests that reality itself may be composed of layers, some accessible to our senses, others only to our reason and mathematics. The force of gravity we feel and the particles we detect are the surface phenomena, the shadows on the cave wall. The vibrating strings and curled-up dimensions are the deeper structure casting those shadows, real in their consequences but hidden from direct experience. This layering extends to our cosmic address. For centuries, the Copernican principle taught us we do not occupy a special place in the universe. Yet, if the landscape of string theory is real, we find ourselves in a strangely special position again, not in space, but in the space of possibilities. We exist in one of the vanishingly rare universes where the constants allow for stars, planets, and conscious life. This does not return us to a privileged center, but it does place us in a privileged corner of a multiversal parameter space, a statistical fluke within a vast ensemble of dead or sterile worlds. This entire journey from Kaluza's fifth dimension to the cosmic landscape demonstrates a profound cycle. Physics does not just discover facts, it actively reshapes our metaphysics, our most basic understanding of existence. Each revolution in theory forces a revolution in philosophy. The current picture humbles us with a powerful insight. Our best scientific image of the world is always provisional. It is a map that is constantly being redrawn as we explore further. The ultimate nature of reality may be a cascading series of mathematical structures, each more fundamental than the last, with our familiar four-dimensional world as a beautiful, emergent layer in that grand architecture. This is not a cause for skepticism, but for awe. It means the universe still holds depths of wonder that defy our intuition, waiting to be uncovered not by looking harder, but by thinking differently. Symmetry is the silent language of the cosmos, a principle of balance and repetition that whispers through the laws of physics. Hidden dimensions are not just extra space, they are the grand stages upon which the most profound symmetries of nature can play out. This connection is the heart of grand unified theories, ambitious frameworks that seek to describe the electromagnetic, weak, and strong nuclear forces as different facets of a single master force. To achieve this, physicists often turn to higher dimensional spaces. Why? Because in the cramped quarters of our familiar four dimensions, the full, beautiful symmetry of this unification simply cannot fit. It requires a more expansive arena, a geometric canvas with more directions, to be expressed in its complete and elegant form. Imagine trying to perfectly arrange a complex, three-dimensional chandelier inside a flat, two-dimensional box. You would have to crush it to break its intricate symmetry to make it fit, but in a room with height, its full glory can be displayed. In a similar way, the mathematical symmetries that unify the forces demand the extra room provided by hidden dimensions. In the searing heat of the universe's first moments, this perfect symmetry reigned. All forces were one, and the extra dimensions may have been unfurled and expansive. But as the cosmos expanded and cooled, a cosmic phase transition occurred, akin to water freezing into ice. The perfect symmetry broke, and as it fractured, the extra dimensions themselves underwent a dramatic change. They compactified, curling up into the intricate shapes like Calabi-Yau manifolds we discussed earlier. This process of symmetry breaking and dimensional compactification is not separate. It is one unified cosmic event. The specific way the symmetry shattered dictated the specific way the dimensions curled. and that curling, in turn, locked in the properties of the forces we now observe. Think of it as a magnificent higher-dimensional crystal. In its initial hot state, it is perfectly symmetric, a flawless gem, but as it cools, internal stresses cause it to shatter. It doesn't break randomly, it fractures along specific, predictable planes, creating a distinctive pattern of fragments. Our four-dimensional reality, with its three distinct non-gravitational forces, is that pattern of fragments. The strong force, the weak force, and electromagnetism are the pieces of the shattered crystal, their properties forever shaped by the lines along which the original, higher-dimensional symmetry broke. This evolutionary narrative ties the entire history of the cosmos to abstract mathematics. The symmetries embedded in those hidden dimensions acted as a cosmic seed, containing the blueprint for everything to come. The cooling of the universe was the trigger, causing that seed to germinate, to differentiate, to unfold into the complex and asymmetric world we see around us. Understanding this profound breaking of symmetry is therefore the key to tracing our lineage. It allows us to rewind the tape, to follow the path from the hot, unified, and likely higher-dimensional dawn of everything to the cool, diverse, and beautifully broken reality we call home. It suggests that the very laws of physics are not eternal commandments, but frozen accidents of history, shaped by the geometry of realms we cannot see. This grand theoretical tapestry is woven not from words, but from an elegant, precise language. To speak of hidden dimensions, we must first master the vocabulary of higher mathematics. This is not a barrier, but a portal. The primary tool is differential geometry, the mathematics of curved spaces. Think of it as the grammar for describing Einstein's warped spacetime or the intricate folds of a Calabi-Yau manifold. It allows physicists to calculate how objects move on curved surfaces, and crucially, how space itself can bend and twist in ways our eyes cannot see. Working hand in hand with this is topology, the study of shapes that remain the same even when stretched, twisted, or deformed, as long as they are not torn. A coffee mug and a donut are topologically identical to a mathematician because one can be smoothly morphed into the other. This concept is vital for understanding compactified dimensions. It tells us that the number of holes in a Calabi-Yau manifold, its fundamental shape, is what truly matters for physics, not its exact pinched geometry. Then there is group theory, the classification of symmetry. It provides the alphabet for writing the laws of particle physics, describing how particles transform into one another under rotations or other operations. In the quest for unification, group theory reveals the beautiful, hidden symmetries that might only become manifest in higher dimensional spaces. The evolution of these fields alongside physics is a story of profound synergy. Often, mathematicians develop structures out of pure intellectual curiosity with no thought of application. Decades later, physicists discover that these abstract forms are the exact blueprints they need. The Calabi-Yau manifold is the perfect example. Mathematicians like Xing-Tung Yau explored its properties for their exquisite internal logic, proving its existence years before string theorists realized these shapes were the ideal candidates for hiding 6 extra dimensions. This interplay reveals a breathtaking truth about our universe. The quest for hidden dimensions is not merely a branch of physics, it is a joint venture with the deepest realms of pure mathematics. It suggests that the architecture of reality is written in a mathematical code so fundamental that exploring its abstract possibilities can predict physical structures long before our telescopes or colliders can hope to find them. To contribute to the next breakthrough, to perhaps one day read that cosmic code directly, means learning to think in this refined and powerful language, where geometry, topology, and symmetry converge to describe worlds beyond our sight. The profound equations and abstract symmetries of this quest are not meant to remain locked in journals. For a scientific idea to truly live, it must breathe in the public imagination. This is the vital, humanizing work of science communication, a crucial chapter in the evolution of hidden dimensions, translating the dizzying mathematics of 10-dimensional strings or holographic boundaries into something we can feel and wonder about requires a special kind of artistry. Visionaries like Carl Sagan did not just present facts, he framed them within a cosmic perspective, connecting the atoms in our bodies to the life cycles of stars, making the vastness of space feel intimately personal. Neil deGrasse Tyson carries that torch, using wit and relatable metaphor to unpack dense concepts, reminding us that curiosity is our birthright. And perhaps no one has done more for dimensional theory than physicist Brane, whose books and documentaries take viewers on a visual journey. He does not simply tell you about Calabi-Yau manifolds. He shows you stunning, computer-generated animations of these shapes twisting and turning, giving form to the formless. He uses the simple analogy of a garden hose viewed from afar to explain compactified dimensions, a mental model that allows anyone to grasp the core idea. This work of translation is more than a service, it is an essential bridge. Documentaries, popular science books, and educational channels transform esoteric research into shared stories. They democratize knowledge, taking concepts born in the rarefied air of academia and planting them in living rooms, classrooms, and coffee shops around the world. This public engagement has a powerful ripple effect. It is not merely about educating a passive audience. It is about inspiration. A teenager watching a documentary on string theory might feel a spark of awe that leads them to study physics. A viewer captivated by the mystery of extra dimensions might support funding for fundamental research. By sharing the wonder and the unanswered questions, science communicators foster a culture that values deep, fundamental inquiry. They ensure the evolution of this field does not happen in an ivory tower, but is fed by a continuous stream of fresh minds and sustained public curiosity. The story of hidden dimensions, therefore, is not complete until it is told. Its next great breakthrough may depend not only on a brilliant calculation, but on a beautifully crafted sentence, a striking visual, or a perfect analogy that inspires the person who will one day make it. Yet every grand vision must withstand the scrutiny of the scientific method. The journey into hidden dimensions, for all its mathematical elegance and explanatory promise, is not without its serious critics and profound challenges. One of the most persistent critiques centers on a core principle of science itself, falsifiability. The philosopher Karl Popper argued that for a theory to be truly scientific, it must make predictions that could, in principle, be proven false by experiment. Some prominent physicists contend that string theory and its extra dimensions, in their current form, fail this crucial test. They point out that many of its most interesting predictions, like the specific vibrational modes of strings or the exact shape of the Calabi-Yau manifold, occur at energy scales so far beyond our technological reach that we may never be able to test them directly. This has led to the sharp criticism that the framework is not even wrong, a phrase meaning it is so flexible that no conceivable observation could rule it out entirely. This is a serious charge touching the very heart of how we define progress in understanding the natural world. Then there is the staggering landscape of possibilities. With an estimated 10 to the 500th power of potential vacuum states, each representing a different universe with different laws, critics ask, does the theory predict anything specific about our own cosmos? If it allows for everything, can it truly explain anything? This abundance of solutions can feel less like a precise blueprint and more like a cosmic phone book where we must simply look up our own entry. Furthermore, the sheer complexity of the mathematics involved has raised questions about whether it represents a unique path to quantum gravity or simply one particularly elaborate and beautiful language among many. These are not dismissals but essential counterpoints that keep the field honest. They force proponents to sharpen their ideas, to search for lower energy consequences we might actually detect, and to grapple with the philosophical implications of a multiverse. This robust debate is not a sign of weakness in the scientific process, it is the process. The evolution of an idea is forged in the fire of criticism. Every objection, every pointed question about testability or uniqueness drives researchers to refine their models, to explore new mathematical avenues, and to design ever more clever experiments. It ensures that the story of hidden dimensions remains a dynamic, living inquiry, not a settled dogma. The ultimate fate of these extraordinary ideas, whether they will be validated as a true description of reality or revised into something entirely new, rests not on their beauty alone, but on their ability to eventually meet the uncompromising gaze of empirical evidence. The search for hidden dimensions is more than a physics puzzle. It is a catalyst for thought across every field of human understanding. This single, profound idea about the architecture of space has sent ripples through cosmology, philosophy, and even the study of the mind itself, weaving a grand interdisciplinary tapestry. In cosmology, the influence is direct and transformative. The very origin of our universe, the Big Bang, is no longer seen as a singular point in a void, but potentially as a higher dimensional event. Some models propose the Big Bang was a collision between two branes floating in the bulk, a cosmic shudder that ignited our reality. Others suggest it was the moment when unstable, unfurled extra dimensions rapidly compactified, releasing the immense energy that drove cosmic inflation. Looking forward, the fate of the cosmos is also tied to these unseen realms. The mysterious dark energy accelerating expansion could be the long-term echo of energy still leaking from the compactified geometry, a slow adjustment of the universe's hidden foundation. Cosmologists now work with equations where the story of everything, from the first instant to the final frontier, is co-written by dimensions we cannot see. This forces a profound philosophical reckoning. For centuries, philosophers have debated the nature of reality, asking what is truly fundamental. The possibility of hidden dimensions, or the holographic principle that suggests our three-dimensional world is a projection, challenges our most basic assumptions. It asks, what does it mean for something to be real? If the truest description of the universe exists in a form utterly alien to our senses, is our tangible, solid world any less real? Or is reality itself layered, with deeper, more fundamental levels giving rise to the level we experience? These are not idle questions, they are urgent inquiries prompted by the cutting edge of physics. They revive ancient dialogues from Plato's cave with a new mathematical precision, forcing us to consider that our entire existence might be played out on a stage we are only beginning to map. Perhaps most speculative, yet fascinating, are the tentative bridges being built toward understanding consciousness itself. Some neuroscientists and theorists note that the brain's vast network of nearly 100 billion neurons, each with thousands of connections, forms a web of staggering complexity. The patterns of thought, memory, and awareness may not be easily captured by models that only consider three-dimensional space. Could the brain's information processing be more naturally described using the mathematics of higher dimensional information structures, like complex networks or shapes that exist in abstract conceptual spaces? This is not to suggest our brains access other spatial dimensions, but that the tools developed to model hidden physical dimensions, tools from topology and geometry, might offer new languages to describe the hidden landscape of the mind. It is a frontier of pure exploration where a concept born in theoretical physics might illuminate the greatest mystery we carry within us. This cross-pollination of ideas is the true mark of a revolutionary concept. The evolution of the hidden dimension hypothesis shows that a breakthrough in one corner of science does not stay there. It spills over, enriching cosmology with new origin stories, challenging philosophy with new definitions of reality, and offering fresh metaphors to those studying consciousness. It reminds us that the quest to understand the cosmos is inseparable from the quest to understand our place within it. The universe is not a collection of isolated puzzles, but a single, interconnected mystery, and each new thread we pull, whether from the fabric of spacetime or the fabric of thought, reveals more of the grand, unexpected design. The cosmos is about to speak in a new language, one of whispers from the very dawn of time. Our next window into hidden dimensions may not be a microscope, but a telescope, as we train an unprecedented array of observatories on the sky. These instruments are not looking for the dimensions themselves, but for their faint echoes, the subtle fingerprints they left on the universe in its fiery infancy. The James Webb Space Telescope peers deeper into the infrared than ever before, observing the formation of the first galaxies. In this ancient light, we may find patterns, unexpected distributions of matter that trace back to the physics of the universe's first moments, a time when extra dimensions were likely unfurled and dynamic. Meanwhile, the Laser Interferometer Space Antenna, or LISA, will open an entirely new sense. This space-based observatory is designed to detect gravitational waves, not from colliding black holes, but from the universe's earliest epochs. It will listen for the faintest ripples in spacetime itself, vibrations that have been traveling since the universe was a fraction of a second old. Among these signals, the Holy Grail would be a detection of primordial gravitational waves, ripples generated by the violent expansion of cosmic inflation. The character of these waves, their specific frequency and amplitude, could carry direct imprints of the energy scales at play during that expansion. And if that inflationary energy was driven by the stabilization of extra dimensions, as some theories propose, then the signature in those gravitational waves would reflect that higher dimensional geometry. It would be a cosmic sonogram of the universe's birth, revealing the hidden structures present at that moment. Furthermore, next-generation experiments mapping the cosmic microwave background, the afterglow of the Big Bang, will examine this ancient light with microscopic precision. Tiny, telltale patterns in its polarization could also betray the influence of primordial gravitational waves, and by extension, the physics of the ultra-high energy realm where dimensions are unified. This transforms our entire approach. We are no longer waiting to build a collider powerful enough to recreate those energies. Instead, we are using the universe itself as the ultimate particle accelerator, one that performed its most energetic experiments nearly 14 billion years ago. By carefully reading the cosmic record it left behind, in the oldest light and the faintest spacetime tremors, we may finally find observational clues to the architecture that birthed everything we see. The sky is not just a spectacle, it is a historical document, and we are just now learning to decipher its most profound chapter. This perspective transforms a cosmic mystery into a question of cosmic real estate. Why do we find ourselves in a universe with precisely 3 large spatial dimensions, a specific strength of gravity, and just the right constants for stars and planets to form? If the landscape of string theory is real, with its countless possible configurations of hidden dimensions, then our universe's specific rulebook might not be the only one ever written. It is simply the one we are reading because it is the only kind that allows for readers to exist. This is the Anthropic Principle in its most profound form. It shifts the explanation for our reality's fine-tuning away from a single, elegant, fundamental law and toward a process of environmental selection on a multiversal scale. Think of it like this. Imagine a vast, dark ocean filled with islands. Most of these islands are barren, scoured by perpetual storms or frozen in eternal ice. A rare few, however, possess a perfect balance of climate, fertile soil, and fresh water. If you are a conscious being walking on an island, you will inevitably find yourself on one of those hospitable few. You would be wrong to conclude that all islands must be this way. You are simply experiencing the only kind of island that could support your journey. In this analogy, each island is a separate universe within the multiverse, born with a different set of compactified dimensions and physical constants. The vast majority are stillborn or sterile, incapable of forming complex structures. Our universe is not special because it was chosen. It is special because we are here to notice its specialness. This idea directly addresses the stability of our three extended dimensions. In the chaotic froth of the multiverse, countless universes may have bubbled into existence with 4, 5, or even all 10 dimensions remaining large and unfurled. But in such universes, the forces of nature behave differently. Gravity might be too strong, causing stars to collapse instantly. The nuclear forces might be too weak, preventing atoms from ever bonding. The very fabric of spacetime might be unstable, tearing itself apart. These universes flicker out or persist as empty, featureless voids. Only in the rare cases where the dice landed just right, where exactly 3 dimensions expanded to a vast scale and the others curled into a specific, stable shape, could the long chain of events leading to galaxies, chemistry, and life unfold. From this evolutionary viewpoint, the hidden dimensions did not compactify according to a grand, predetermined plan. Their specific configuration was a random outcome, a roll of the cosmic dice at the moment of that universe's birth. The evolution we speak of, then, is not a directed march toward complexity, but a blind exploration of possibility, with conscious observers like us emerging only in the rare, stable niches where the numbers line up. This forces a deep and somewhat unsettling reconsideration. For centuries, the goal of physics has been to find the single, beautiful equation that uniquely predicts everything we see. The anthropic landscape suggests there may be no such unique prediction. Instead, the fundamental theory might describe the entire multiversal ocean, while our local laws are more like the weather patterns on our particular island, contingent and not uniquely special. The explanation for why things are the way they are becomes statistical, not fundamental. It is a shift that challenges our desire for a neat, causal story, replacing it with a grand, probabilistic tapestry where our existence is both miraculously unlikely and, in the vastness of all possibilities, almost inevitable. The journey from wonder to discovery requires a map of its own. For those feeling the pull to become explorers of these hidden realms, the path is both demanding and deeply rewarding, a calling that merges abstract beauty with the rigorous pursuit of truth. It begins with building a strong foundation, a process of learning the language the universe speaks. An undergraduate degree in physics or mathematics provides the essential alphabet, introducing the core principles of classical mechanics, electromagnetism, and calculus. This stage is about learning to see the world not just as it appears, but as a set of elegant, describable interactions. From there, the path narrows and deepens. Graduate studies become the gateway where you choose to focus on the frontiers of theoretical high-energy physics, cosmology, or mathematical physics. Here, the textbooks of your undergraduate years give way to the living, breathing edge of research. You will immerse yourself in the masterworks of modern theory, mastering the intricate frameworks of quantum field theory, which describes particles and forces as excitations in fields, and the profound geometry of general relativity, where gravity is the curvature of spacetime itself. A crucial and beautiful tool in this toolkit is differential geometry, the mathematics of curved spaces. Think of it as learning to navigate not on flat paper maps, but on the surface of a globe or a twisting manifold, a skill absolutely vital for charting unseen dimensions. But this journey is not one of solitary study alone. True exploration happens in conversation with the frontier itself. This means engaging directly with the primary literature, the research papers where new ideas are first proposed and debated. Attending seminars and conferences is equally crucial, places where you can hear from the thinkers shaping the field, ask questions, and begin to build your own network of fellow travelers. The evolution of knowledge in this domain is breathtakingly rapid. A concept that is speculative today might be foundational tomorrow, or it might be refined into something entirely new. This demands a particular mindset, one of intellectual courage and humility, coupled with a commitment to lifelong learning. You must be comfortable not knowing and find excitement in the questions more than the certainty of answers. By walking this path, you are doing more than building a career. You are preparing to contribute to the next chapter in humanity's oldest story, the quest to understand where we are. You join the unbroken lineage that stretches from the philosophers of the ancient world to the theorists of today, each one expanding the horizons of what we believe is possible. Your curiosity could one day help decipher the cosmic blueprint, adding a new line to the map of reality's hidden architecture. The search for hidden dimensions might seem like a purely abstract exercise, a game for theorists playing with equations far removed from daily life. Yet this profound quest has always been about more than just satisfying our deepest curiosity. It sparks tangible progress that ripples through our world. Consider the mathematics required to describe these complex, higher-dimensional spaces. The intricate tools of topology, differential geometry, and group theory, sharpened to a fine point by theorists, have found surprising and powerful applications far from their origins. The same abstract structures used to model Calabi-Yau manifolds have been applied in the field of cryptography, helping to design more secure methods for encoding digital information. In materials science, concepts from string theory have provided fresh insights into exotic states of matter, like superconductors, offering new mathematical lenses to understand their bizarre properties. This is a recurring pattern in the history of science. Pure inquiry, driven by wonder, often builds the intellectual tools that later solve practical problems we never anticipated. But the impact runs deeper than technological spin-offs. This evolutionary journey of ideas represents something fundamental about our species, our relentless drive to understand our place in the grand scheme. From ancient stargazers to modern physicists running colossal experiments, we are compelled to map the architecture of existence. This pursuit does not just fill textbooks, it enriches our entire culture. It inspires art, literature, and philosophy, feeding a sense of awe that reminds us the universe is far stranger and more wonderful than our ordinary concerns. It demonstrates the extraordinary power of human reason and imagination to probe realms forever beyond our direct senses. By valuing such long-term, fundamental exploration, we foster a society that prizes knowledge, critical thinking, and patience. We invest in the capacity to ask better questions, which is the bedrock of all future discovery. The benefits of this quest, therefore, transcend any immediate gadget or application. They are woven into the fabric of a civilization that looks upward and inward, choosing to marvel at the hidden layers of reality and daring to decode them. This grand pursuit has a name: the quest for a theory of everything. It is the silent engine behind every leap from Kaluza's fifth dimension to the vibrating strings of 10. The dream is breathtaking in its simplicity: to find a single, coherent framework, a master equation from which all the laws of nature, every force and every particle, can be derived as a natural consequence. Think of it as the search for the universe's source code, a pristine set of instructions written not in ones and zeros, but in the elegant language of geometry and symmetry. Each theory of hidden dimensions represents a bold attempt to compile this code, to see if the program runs without error. Kaluza-Klein theory was a stunning first pass, showing how adding one unseen dimension could make gravity and electromagnetism speak the same mathematical tongue. String theory took the ambition further, proposing that every ingredient of reality is a note played on a microscopic loop, with the hope that the entire cosmic symphony would emerge from its harmonies. M-theory, the enigmatic successor, hints at an even deeper, 11-dimensional structure that might unify all known versions of string theory under one roof. This is not merely technical tinkering, it is one of the most profound adventures the human mind has ever undertaken. We are trying to read the cosmic blueprint, to understand the foundational architecture upon which everything from the spin of an electron to the whirl of a galaxy is built. And the consistent, recurring clue in this detective story has been the necessity of extra dimensions. They are not an optional flourish, they appear to be essential structural elements, the extra rooms and hallways needed for the full theory of everything to reside. The journey toward this ultimate synthesis has reshaped our very conception of reality. It has taught us that space and time are not a static stage, but a dynamic, possibly emergent participant in the cosmic drama. It has shown that matter and force might be secondary phenomena, vibrational echoes of deeper geometric truths, while the final, complete theory remains just beyond our current grasp, shimmering like a mirage on the horizon. The path toward it has been littered with revolutionary insights. Each step, each proposed set of hidden dimensions, has forced us to rewrite the textbooks, to expand our imagination, and to accept that the universe is far stranger and more cleverly constructed than we ever dared to suppose. This process itself is the heart of science, a relentless, generational effort to approximate a truth that may always recede as we approach. We stand on the discoveries of those who came before, adding our own piece to the puzzle, inching closer to a vision of cosmic unity written in the hidden folds of the world. Yet this monumental quest does not unfold in a vacuum. The search for hidden dimensions, with its colossal particle colliders and decades of abstract theorizing, carries its own weight of ethical consideration. When we invest billions and marshal the world's brightest minds to probe the fabric of spacetime, we must pause and ask, is this the right priority for our time? The question is not trivial. Our world faces urgent, tangible challenges, from environmental shifts to health crises and global inequity. The resources and intellectual capital devoted to understanding cosmic strings or 10-dimensional manifolds could, on the surface, seem like a profound misallocation. This tension forms a critical part of the story's evolution, a necessary reflection on why we do what we do. The ethical calculus is complex, but history provides a powerful counterpoint. Time and again, the pursuit of pure, fundamental understanding has yielded gifts we never anticipated. The entire framework of the World Wide Web was invented at CERN, the home of the Large Hadron Collider, not to create a global communication network, but to help physicists share data. The precise mathematics developed for general relativity later became essential for the GPS satellites that guide our daily travels. Lasers, born from theoretical quantum mechanics, now enable everything from eye surgery to manufacturing and entertainment. These were not the goals, but the unforeseen dividends of asking deep questions about how the universe works. The tools we forge to explore the abstract often become the very instruments that transform our concrete world. Beyond practical spin-offs, there is an intrinsic value to this kind of exploration that defines a civilization. The drive to understand our place in the cosmos, to map reality's hidden architecture, is a profound expression of human curiosity and resilience. It fosters unprecedented international cooperation, as seen in projects like the LHC, where thousands of scientists from over 100 countries work together across borders, united by a shared question. This collaborative spirit builds bridges of knowledge and diplomacy that extend far beyond the laboratory. It cultivates a global sense of wonder, reminding us that we are part of a story far grander than our immediate struggles. The ethical evolution, then, is not about choosing between fundamental science and applied solutions. It is about maintaining a mindful balance, It requires championing the irreplaceable value of discovery for its own sake, while ensuring that such grand projects proceed with transparency, inclusivity, and an awareness of their context in a world with many needs. It means communicating not just what we find, but why the search itself matters, how it enriches our culture, sharpens our intellect, and occasionally, quite miraculously, hands us the keys to solving problems we did not yet know we had. This balanced perspective ensures that our reach toward the cosmos remains grounded in a deep respect for the world and the people within it. The true reward of this journey lies not in a final answer, but in the permanent expansion of your own perspective. Learning about hidden dimensions does more than fill your mind with fascinating concepts. It actively rewires how you perceive the world around you. It is an exercise in building new mental models, frameworks for understanding that stretch far beyond the limits of your immediate senses. You are training yourself to think in geometries that cannot be visualized, to embrace paradoxes where a particle can be in two places at once, and to see the profound beauty encoded in complex, abstract mathematics. This intellectual journey you have undertaken mirrors the cosmic evolution we have traced. Just as the universe unfolds from a hot, symmetric state into the rich diversity we see, your understanding has likely unfolded from a simple, three-dimensional view into a far more layered and mysterious vision of reality. Each layer peeled back, whether it is the compactification of a Calabi-Yau manifold or the holographic projection of our world, reveals a deeper, often more elegant truth beneath. By choosing to engage with these ideas, you have done something remarkable. You have actively participated in the grand, collective human project of understanding. This is not a passive act of watching a documentary. It is an active cultivation of a mindset. It is a practice of curiosity that questions the solidity of the stage beneath your feet. It is an exercise in humility that acknowledges the vastness of what we do not yet know. And this mindset, once nurtured, does not stay confined to cosmology. It spills over. It changes how you approach problems in your own life, encouraging you to look for hidden variables, to consider perspectives beyond the obvious, and to find elegant solutions within apparent complexity. You begin to carry a sense of cosmic awe with you, a quiet awareness that the ordinary world of tables and chairs and sunlight is the most extraordinary interface with a reality of unimaginable depth. This is the lasting gift of the exploration, a transformed way of seeing that turns every moment into a point of contact with the hidden architecture of everything. Our journey through the hidden folds of reality has been a testament to the audacity of human curiosity. We began with the flickering shadows in Plato's cave and the abstract geometries of 19th century mathematicians, then traced the revolutionary ideas that dared to rewrite the cosmic blueprint. We saw how Einstein wove time into a four-dimensional fabric, how Kaluza and Klein glimpsed a fifth dimension to unify forces, and how the crisis of quantum gravity gave birth to strings vibrating in 10. We explored the possibility that our universe is a three-dimensional brane adrift in a higher dimensional bulk, and that the very weakness of gravity might be a clue written in this unseen architecture. This evolution from philosophical wonder to precise mathematical theory reveals a profound truth. These hidden dimensions are not science fiction. They are serious, rigorous attempts to answer the most fundamental questions we can pose. They strive to explain why our universe has the laws it does, what powered its explosive birth, and what mysterious force now drives its accelerating expansion. The final, definitive proof, the experimental signal that confirms their physical reality, remains the great challenge ahead, a frontier for the next generation of cosmic detectives. Yet, even in the waiting, the theoretical journey itself has irrevocably transformed our story. It has shown us that the cosmos is likely far stranger, more elegant, and more deeply layered than our everyday senses could ever suggest. It reminds us, as Einstein once reflected, that the most incomprehensible thing about the universe is that we can comprehend it at all. This relentless pursuit of understanding, this mapping of reality's hidden blueprints, is a beautiful expression of that very comprehensibility. If this exploration has reshaped how you see the space around you, we would love to hear your reflections in the comments below. For more journeys to the edges of our understanding, subscribe and join us as we continue to look up at the stars and inward to the profound architectures they hint at. Keep wondering.